Put me in, coach. Just kidding. Okay. All right, so we are going to work with substitution again today, but we're going to go to a different part of our book. You're going to get problems that are from Chapter 5, where we talked about logarithmic and exponential antiderivatives. Okay, so that's really where our substitution is going to come from today. All right. So sometimes we need to look at, when you see this up here, you don't think of this probably as a composition of a function, okay? But really it is, because we have a fraction, we have something in that 1 over x function. So it doesn't have to be an obvious composition. Sometimes we have a fraction to where our denominator is a perfect candidate for u substitution, okay? What do you notice about the relationship from the denominator to the numerator? Okay, the denominator has an extra exponent, which means their derivatives could be the derivative's pretty close to the numerator. It differs by that constant out front. And that's a relationship that we want to look for with u substitution, right? If we have a u, we want that du to be somewhere there. So go ahead and write down this example. This is the first one we're going to do. But I want you to understand that not always are we going to get a composition in our antiderivative that is obvious. Okay. Now, before we go through this problem right here, I want to write up this one. Okay. If you had something like this on Tuesday, what would you have done with it? You would actually divide by that x, or bring that x up and multiply the x to the negative 1 through. Okay, that would be a very easy thing to do and use our power rule. However, when we have this over here, we don't have that option of taking that denominator and multiplying it through, because there's more than one term. When there's more than one term in the denominator, we really are pretty stuck with it. So what we can try is we can let u be that denominator. Okay. And if things align right, then our numerator can help us out. So du in this case would be 2x dx. All right, well, what do we have in our integral? Do we have 2x dx? So the derivative of x squared plus 1 is 2x. Did that answer your question enough?
Yes.
Okay. So we don't have exactly 2x dx, but what do we have?
X.
We have x dx. Okay? So we can replace x dx with 1/2 du to balance it out. Do you want me to go through that? Okay. And then the u is in our denominator, and so I'm just going to write it as 1 over u. So we have 1/2 times 1 over u du. How do you feel about that? That's okay? Well, what is the antiderivative of 1 over u? Okay. Natural log of the absolute value of u plus c. Okay. That absolute value is very important unless it doesn't matter. What do I mean by that?
I'm sorry, it was just very
Well, it's
it's
kind
not
of
important if it doesn't matter. Yeah, okay.
this is what I mean by that. X squared plus 1. Are we ever going to have an issue with that being positive? I mean, negative. Okay? That's always going to be positive. So when I write this, I really don't have to put the absolute value because x squared plus 1 is always positive. That would be redundant if I have the absolute value of x squared plus 1. Do I mind if you are redundant? Not at all. But in a multiple choice type of question, they're probably not going to have both the absolute value with the x squared plus 1. So I just want you to I want to make you aware of that. Now, if it were like x squared minus 5, you better have the absolute values there. All right. Well, let's look at another one. Let's see. Okay, what are your thoughts about this problem? So Brinley notices that secant squared x is the derivative of tangent of x. That's kind of nice, isn't it? Which means, what can we do? We can let u equal the tangent of x because our derivative, secant squared x dx, is in that integral. So secant squared x dx is there. We can replace it with du. So all we have is 1 over u du. That works out really nice, didn't it? So our antiderivative is the natural log of the absolute value of u plus c. And here you would need to keep the absolute values because the tangent of x has a range of all real numbers. Okay? 3 more examples. Oh, where does this one come from? Oh, okay, 4 more examples. There you go. Write this one down. Sorry. Make some observations of this problem with your neighbors. Did you find something that was crazy? The derivative of x natural log of x is a product. Yeah. Not as cool as you thought.
No.
All right, Ellie-Ann, what did you notice? Okay, the derivative of the natural log of x is 1 over x. Do you see 1 over x in there? Yeah. So what can happen if u is the natural log of x, du is 1 over x dx, which technically we have 1 over x dx. If you don't see that relationship, there's nowhere else to go. Okay? So thinking about those relationships and how U substitution works is sometimes important in finding those patterns for us to be able to do it. All right? So 1 over x dx becomes du. The natural log of x is u. So our antiderivative is the natural log of the absolute value of u plus c. So when we plug in u, we get the natural log of the absolute value of the natural log of x plus c. That's a fairly popular problem. Like, that's probably not the only time you'll see it. Now we have 3 more. And people will at least get 2 of them in with you. Maybe all 3. I don't know. Do we have a simple antiderivative for tangent of x? We don't. What did you say, Celine? We know that tangent is sine over cosine, so maybe that can help us. So let's write it. Trig identities to the rescue. Okay, so Celine suggested this. Why is that helpful? Okay, we have that derivative relationship going on from denominator to numerator. All right, so what we can do is we can let our denominator be u. So u is cosine of x, which makes du Yes. Let's talk about that. So we have sine of x dx, which means we can replace it with negative du, and this becomes 1 over u. Now, over here, I'm going to do it here on the board. If we let u equal the sine of x, du is cosine of x dx, we don't have cosine of x dx in our integral. We have 1 over cosine of x dx. Okay, and so that relationship's not going to work.
Can it always be the bottom?
If you have a fraction where u substitution is going to work, I'm going to say 99% of the time. Okay. Now, if you have something like the natural log of x over x, that is one case where it would not work out that way. So we have negative natural log of the absolute value of u plus c, which we would then throw in the cosine of x plus c. Here is our antiderivative for tangent. If I remember correctly, either you have cotangent in your homework over the weekend, or that will be our warm-up problem on Monday. Tangent and cotangent both have to be written as fractions, and then we use u substitution for it. Okay, Ben, I'm trying to get you as many examples as we can here. We're in here until 25, the rest of us. Okay, so here's a fraction, and today we've really been working with like our fractions being set up really nicely for u substitution, but this one really isn't, is it? No. What kind of fraction are we working with? What makes it improper? Okay, we have an improper fraction because our numerator is larger than our denominator. What can we do with an improper fraction? If we could factor out x minus 2, that would be really cool. But instead of factoring it out because it doesn't factor out evenly, we make it a mixed number by doing what?
I guess I was right. Oh. You're pulling that thing out. I'm not.
You haven't seen it in a year because you did it in pre-calculus. I know this. We did it.
Oh, I forgot.
We can actually divide, right? If you had 5/4, 5 divided by 4 is 1 with a remainder of 1. So you write 1 1/4, right? So all we have to do is some division. I will help you through this. It's not a big deal.
This is why we took pre-calc. This is the
Celine, have you ever seen?
Yes, but I've never
Okay.
thing.
Here's your chance.
Welcome to
Are you ready?
the-
All right. X. Okay, look. X times what is 2x squared? 2x. So we're going to put that in the x column. Okay. And then this guy right here gets multiplied to that number that we just wrote. X times 2x is 2x squared. Negative 2 times 2x is negative 4x. What do we do with those quantities? We subtract them. So Mrs. Holman likes to just change signs so I don't have to keep track of the subtraction. And we're left with 11x, and we bring down the next number, minus 3. X times what is 11x? So then we take 11 and multiply it by our divisor, x minus 2. So we have 11x minus 22. And we're subtracting, so I'm going to change the signs. And we have a remainder of...
Teachers, at this time, please release the band and color guard to get ready for the pep rally. Again, at this time, please release the band and the color guard. Thank you.
Okay. So, real quick before you go, Band Peeps, we have the antiderivative of 2x plus 11 plus we had a remainder of 19, so we're going to throw that over our divisor.
Have a good day. See you later, guys. Have fun.
Play loud. And on please. Can you throw the flag? All right, Celine, are you okay with what we did? Okay, so now antiderivative of 2x is x squared plus the antiderivative of 11 is 11x plus, since this is linear, you can do u substitution, but we wouldn't have to. This is dx. It just didn't. So then this antiderivative is 19 natural log of the absolute value of x minus 2 plus 0. Right? If 1 over x antiderivative is natural log of x, then 1 over x minus 2 antiderivative would be natural log of x minus 2. You see what I mean by that? All right. Questions on that one before we do our last example? All right, let's do our last example. Do they still have fruit stripe gum? You know what I'm talking about?
I forgot about
Those
that.
are horrible. They last like
They last like 10 seconds.
But they were fun.
No. Bazooka gun.
the,
No, like the big squares.
yeah, those are awesome.
Those are
You could put like 3 in your mouth.
I know, I would always put so
Yeah.
Okay, now technically there are a couple different ways to go about this problem. Okay, you could multiply out that squared binomial, or we can understand that we have a composition and what is inside of our function is related to what's outside of our function by a derivative, so that would be helpful for u substitution. Okay, we could let u equal the inside e to the x plus 1, because what's our antiderivative? Or what's our derivative? E to the x. Okay. What's tricky about u substitution is you have to think antiderivative and derivative at the same time. Okay. So those derivatives that we worked on for so long, okay, we can't just like forget about them because we're using them even as we're going backwards. Okay. So we have e to the x dx that we can replace with du. And then this just becomes u squared. So this is just u squared du. So we have 1/3 u cubed plus c. And we replace u with what we set it equal to, and voila, we've got it. Okay, we have about 10 minutes before we go to the pep rally. So I think it would be a great idea if you did about 2 to 3 problems to make sure that you're on the right track with this before we get released.
So when I go to the restroom,
Probably like a $1,000 credit card. Or those $5.